Hello! So, in this video we're going to be talking about rearrangements. Specifically, when can we do them and how do we do them? So, I'm going to start out sort of motivating the sort of notation and the mechanism of a rearrangement and, defining them. But then editing magic, erasing and such, and we will have a theorem and its proof as well about rearrangements in the case of absolute convergence and how those work. Okay, so what is a rearrangement? So the idea here, and if you remember sort of way back at the beginning, one of the things we talked about was motivation, about how we had the same sort of infinite sum, and I grouped it together and moved stuff around, and I got very different answers as in terms of what they should add up to. And so that moving things around bit, that's what the rearrangements are. So typically thus far, we've looked at things that look like some sort of sum of an, right, n going from 0 to infinity. And we talked about the way of doing this is to look at the partial sums, Sn, where you have something, right, the little Sn is a0, a1, a2, etc. up to an. Okay? Now, we have several times already now in various proofs done various groupings and rearrangements of Sn. Right, so I could say, okay, well, one way I could calculate Sn is to look at it as, say, a0 plus a1 plus a2 plus etc. Maybe it would be even, right, so this is all theoretical, but maybe I could even do something like a5 plus a3 plus a4 if I wanted, right? And so I could do all kinds of manipulations with Sn. But the sort of reason we're using Sn, the reason we're using partial sums, is that it's a finite sum. And if I have a finite sum, then I can use all my normal addition rules, right? I can rearrange them, I can, so that's the commutative property, right? I can use the associative property, I can group them with parentheses, so I can add certain things together before other things. So when I have a finite list, all of this stuff works great, right, for Sn. So a rearrangement is taking this idea past the finite, right? So what we would call in mathematics transfinite. Not that you need to know that for this class, but the point is that the rearrangements, as we're going to describe them, is now going past the point of just looking at some Sn and manipulating Sn specifically. So rearrangements is some mechanism of taking, say, a0 plus a1 plus a2 plus dot dot dot, where that dot doesn't end, right? And then somehow, I'm going to write a little question mark here, somehow I want to rearrange these into some way where I will have the same sum, but in a different order, right? And I'm going to say same sum in quotes, because whether it's the same sum or not is actually a thing we have to explore. But the same sum, meaning the same terms that I'm adding together, but in a different order. So maybe I put it in the order of, let's say, a2 plus a3 plus a5 plus a7 plus, so I do like all the one-digit primes, and then the rest of the one digits in order. So a1, a4, a6, a8, a9. And then maybe I do all the two-digit primes, a11, a13, a17, etc. And then all of the two-digit non-primes, so a10, a12, a14, etc. Right? But the thing is how this works. It's not really something I can demonstrate nicely with an Sn, because I'm breaking apart things all over, right? Or maybe I could do something where I'm going to list 5 primes, then 5 non-primes, then 5 more primes, then 5 more non-primes. And with the way primes are spaced out, I'm going to have to go really big numbers to get more primes eventually, even though I'm still working on the relatively speaking, smaller non-primes. So these rearrangements are ways of reordering these things where it doesn't necessarily work as well trying to do something about S capital N, because I need to sort of go and pick stuff that's arbitrarily far down the line before I come back and grab the stuff early, right? So to be clear, like if I want to do A4, for example, in order to do the sum, I was supposed to do A5 and A7 before I did A1 or A4. So S4 doesn't really make as much sense anymore in this sum, right? Because I need stuff past A4 before I can use A4. This is the idea. So rearrangements are a way of moving around all the terms, potentially. I don't have to move them all, but it's a way of doing that as an option. So this leads us to the question of how do we make this rigorous? And even what does it mean to be rigorous, right? So the questions we have to ask ourselves essentially is what features do we want rearrangements to have, right? So for one, I still need to use all of the terms, right? I can't really claim that I'm rearranging the terms if suddenly, say, A5 disappears, right? So I need to use, I'll put this in quotes, use all terms. And by use, what I really mean is I need to know that every term has a place. I don't necessarily need to move every term, right? A5 could still be the fifth thing I'm adding, but I need to know that A5 is somewhere, right? Somewhere in the chain of sums, okay? Next thing for rearrangements, I need to know where a specific term is. So by this we mean that the whole point of being rigorous is that somebody else could reproduce this, right? It needs to be objective. So I need to be able to come up with a system where not only do I know A5 was used, but I can describe where I put A5 in a way that everybody else will put it in the same exact spot, right? So if I'm looking at this, for example, up here, I could say, okay, A5 is in the fourth spot, and then everybody else, right, because I have 1, 2, 3, 4, everybody else will then do the same thing. A5 always ends up in the fourth spot, right? So I need to know where each specific term is. I need to make sure all the terms get used. And, sort of last but not least, I can't have duplicate terms. And by this, what I mean is not that I can't have 2 twice. It's that I can't have A5 twice, right? So it might be that I could have more than one index that has the same value. A5 might be the same as A17, and that's okay. But when I describe this, and this is sort of inherent in the previous ones, when I describe this, I need to know where the specific term A5 is, but it needs to be in a specific spot, right? I need to say like A5 is the 4th item, not A5 is the 4th and 10th item. That doesn't work because, again, the original is adding up, just the one of each, and so any rearrangement should have one of each. It shouldn't have duplication, right? So what we want is some way of putting all this together, and it turns out we actually already have a tool for this. It's just not something that you're used to seeing in this context. So let me give myself a little space off to the side here, now that we don't really need that example. So what we want to use is called a bijection. So in case you don't remember, bijections, these are functions with a domain and range And I'm going to deliberately leave that blank for a second. So it has a domain, has a range, but it also has two further properties. And really 3 properties because I said it's a function. So first, it's a function. So what does that mean, right? Remember the technical definition of a function from pre-calc, if nowhere else. It's a function means that each input has exactly one output, right? So each input has exactly one output. Okay, so bijection, again, if you don't remember, these are one-to-one and onto. So one-to-one function is saying that that one-to-one property, so this idea that each input has exactly one output, works in both directions. So each output came from exactly one input. So each output has a unique input. So for example, if I have a one-to-one function, right, so this is the one-to-one property. If I have a one-to-one function, and I know that I have the point 2, 7 on that thing, right? That's saying the input is 2, the output is 7. So the y value is 7. The one-to-one property says that nowhere else has a y value of 7, right? If you remember, for example, as a 2-second drawing, the x squared function, right? You can get y equals, say, 4 in 2 places, right? So this is not a one-to-one function, and the way you know it's one-to-one from an xy perspective is that it would pass a horizontal line test, right? The function's the vertical line test, the horizontal line test is the one-to-one. With how we're going to use this, the graph isn't a great analogy because it doesn't graph quite as well as you might hope, but just building intuition here. So each output has a unique input, right? Each thing only shows up in one place for the domain, for the range, excuse me. And the other thing for bijection is that it's onto. So what does that mean? That means that every element in the codomain is actually hit. So every element in the codomain has some domain value that maps to it, right? So every element in the domain, codomain, here, I'll write it sort of better terminology, is the image for some element in the domain. Okay, so my claim is that the bijection does what we want, and the question is, why or how does it do what we want? So let's think about this for a second. If I were to give a rearrangement of these things and try to describe it, how could I do that? Well, perhaps the sort of most straightforward way of doing it would be to do what I said earlier, where I just tell you, okay, this thing is the first one, this one is the next one, this one is the next one, right? So I'd say, in this case, with this rearrangement, A0 is the first thing to write, then A1, then A2, then A5, then A3, then A4, etc., right? Obviously, I can't necessarily do that all the time, right? If I'm trying to describe infinitely many things, I can't possibly list infinitely many things. But what I could do instead is write something that tells you if this is the input, this is this is the corresponding output. If you're looking at where to put A17, you could put it in the 23rd slot, right? But if I think about it, the A part isn't doing anything there. I know they're all A sub something. What I care about is the index. The index where it's starting from and the index and where it goes, right? So for example here, right, A2 is going to be the 0th term. So I want something that says, okay, 2, right? So if I look at this line here as I have it written, let me write it maybe over here. This is saying, okay, 2 goes to 0, because 0 was the first element, right? And then 3 is now the first element, 5 is now the second element, right? And really, I can think of it as 2 gets moved to that spot, 3 gets moved to that spot, 5 gets moved to that spot. Or I can go the other direction and say the 0th element is 2, the first element is 3, the second element is 5, right? Either direction is fine. The point being that that's exactly what's happening with the bijection. It's going either direction, but the key here is that the bijection is not on the elements themselves. I don't care that A0 is a 2, right, or let's say A0 is pi. I don't care that the sort of 0th element became pi or is getting moved elsewhere, right? Like if A2 is E squared, I don't care that E squared got moved to the 0th position. What I care is that the A2 got moved to the 0th position. So the bijection is actually a bijection on the natural numbers, because really what this is that it's a bijection on the index of the elements. Because the rearrangement is telling me where to put stuff. And so the bijection is a description of where I'm putting things, which is all about the index, okay? And if I think about it in that term, you can actually link up what's happening here, right? It's a function. Each input, that's the original index, has exactly one output, the new index, right? That's telling me that if I have a thing, I need to know where it goes. Well, I need to use all the terms, but I need to know where the specific term is going, right? So I guess 1 actually links up to 2 here. Each output has a unique input, so that's telling me that if I use something, I'm going to use the sort of only that thing once. I can't have duplicate outputs. But that's exactly what number 3 was. I can't have duplicate terms. If I have an output of the 7th index, then that can only go to one spot because it's got a unique piece, right? The 7th one is got to go to that specific output and the other, and vice versa. And the 3rd one, every element in the codomain is the image for some element. That's telling me that everything over here has some place that it goes to. So what that's telling me is, and again, vice versa, that's the whole point of the bijection. So what that's telling me is that everything has a place, and that's number 1, okay? So this idea of a bijection, it feels sort of arbitrary, and the notation seems kind of weird when you first run into it, but it's actually exactly the natural thing that you would want. Again, it's just an issue of the sort of notation maybe obscuring the intuition a little bit, which is why we did this description. Okay, so with that, I'm going to do some editing magic, and we will go through a theorem. And actually, I'll probably just, to be honest, probably just end the video here, and we'll do the theorem in its own video. That way you guys have this by way of reference if you need it. So I guess I will end the video here and do the video in its own, the theorem in its own video.